Welcome back. So we were talking about min-max optimizations and their differences with minimization. And from the perspective of basically dynamical systems, we saw that the main difference and the main issue preventing simple methods to work well in the min-max setting and training of GANs is that the dynamic associated with optimization problems, minimization problems, is actually quite nice. In the sense that it is purely symmetric, has a purely symmetric Jacobian. On the other hand, for min-max problem, the dynamic has a skew-symmetric component, which basically pushes our solution around and potentially away from the stable point, from the equilibrium. Okay, and now we want to talk about how we can fix that. And the main idea is what we call negative momentum optimism and predictability, basically. Recall, we talked about momentum previously. We said that, well, I know gradient direction is a good direction, or the negative gradient direction is a good direction for minimization. Well, we can sort of double down on that by introducing positive momentum. Okay, so this is what we discussed last time. We talked about, for instance, the heavy wall momentum method, Nesterov momentum, and also their connection to bias variance trade-off, and the nice advanced training algorithms that we use in practice. Okay, so the idea is that, again, a gradient direction is useful. If we double down, we can have positive momentum, okay, and use that for faster convergence. For min-max problem, however, as we talk about, the local direction, let's call it the gradient direction, if you will, is not good, is not useful. Okay, so it has a mistake. So if we leverage positive momentum, we're going to actually make more mistakes. So if we were, let's say, slowly circling and going away from the equilibrium by using a positive momentum, we're going to actually move away even faster. What we can do, however, is to correct the direction of the gradient by using negative momentum. So inherently, the direction has some mistake. Now, I don't want to use positive momentum to make more mistakes. I make negative or use negative momentum to fix that mistake. Okay, so that's the main idea. Now, the main question, the big question is, how can we fix this issue? Okay, well, let's try to look at this figure. Okay, so think of this as, again, the dynamics associated with the general system that could have both symmetric and skew-symmetric components in the Jacobian. Now let's say this diamond is my stable point, and this is where I start. Okay, so the direction of the gradient is not useful. The direction of the flow is not useful, and if I follow this direction, I'm gonna circle around the equilibrium and even potentially start to go further and further away. Okay. Now this is the gradient, let's say, at the initialization. Let's look at the direction of the gradient in future. Okay, so the direction of the gradient in future is again here. Okay, so which means that, again, if I were to use the direction of the gradient, this future gradient, the blue one, at this point, I'm not gonna converge anymore, right? So I'm not gonna find anything useful. But let's see what happens when I transform transport this gradient at this future point. So let's call this, let's say, W1, and let's call this point W2. So what happens when I shift or transport this gradient at W2 to the one at initialization? Well, I just shifted that, and now it is here. So therefore, this is, as you can see, is pointing inward. It is kind of pointing toward the equilibrium, such that if instead of the gradient at W1, I use the gradient at W2, I might actually be able to go to the equilibrium. Okay, so this is the gradient at W1. So let's denote that with F1. Okay, and this is F2. So what I'm saying is that let's use F2, not F1, to update the parameter, given that from these pictures, it is a more useful vector. It is pointing inward toward the equilibrium, whereas the usual gradient is actually pointing away from the equilibrium. Okay, so this idea leads to this update, where you go from the current solution to the next one by following the gradient or the flow evaluated at the next solution. Okay. So there is actually a connection between this method and the Euler discretization, as well as an elegant idea in optimization. So let's talk about that. So it turns out, and as I'm going to show in the next slide, that this update that we are talking about here is precisely what we call the Euler backward discretization, as opposed to Euler forward discretization, which leads to gradient descent. So this is another way to discretize the continuous time dynamics. Okay. And in general, as it is readily seen, this is going to be an implicit update. So it means that if I want to find the next update, I have to solve a nonlinear system of equations, because capital F in general is could be highly complex. Okay, but for certain applications, this capital F is actually something that leads to an explicit update. For instance, min-max problems such as bilinear games, something like this. So for this, you can kind of have, if you can afford a matrix inversion, you can say that I have like a easy to compute update. Okay. So that's basically one connection, the connection to a different kind of a discretization, Euler backward discretization, and also noting the fact that in general this is an implicit update. So in general we cannot use this, so we have to come up with approximation of this update, as we're going to talk about next. Okay. And the second thing I want to point out here is that there is actually a connection between this method and a method from optimization, in particular for minimization problems, which is called the proximal point method. So why is it called the proximal point method? Well, if you replace this capital F with the gradient of some scalar convex function f, what you can show is that the update that I've written here, this implicit update, is actually equivalent to what I've written here on the right-hand side of equation 20. So the next solution is basically tries to minimize the original function plus some regularization term that aims to ensure we remain in the proximity of the current solution WT. That's why it's basically called the proximal point method. And again, in general, solving this problem is also as hard as solving the original problem. Okay? So in general, this is also an implicit method, unless F has some nice structures. Okay, so at least hopefully intuitively now we can see that we have a fix. The fix essentially is to use predictability, use the direction prescribed by the next update to update the current solution. This leads to the method that we call proximal point method, and it turns out that this method will actually work well in the sense that it can find the equilibrium, even though the simple gradient descent method cannot. However, the main issue is that it is implicit in general and it's not quite efficient. So what we're going to do then is to introduce two approximations to this proximal point strategy. Okay. So to motivate these approximations, first I want to talk about the first method, which is called the extra gradient method. And I want to kind of view this as a different kind of discretization of the same ordinary differential equation. Okay, so let's consider our flow in the continuous time limit. So the derivative of v with respect to time is just minus the flow. Okay, and if you take the integral from both sides, this is going to be equivalent to what I've written on the right-hand side of equation 21. Okay. Now, we haven't done anything. So solving this integral is as hard as solving the original ODE. Now, what do? Well, we do approximation. We do discretization in particular. Okay. So one thing you can do is the simple forward Euler discretization, which tries to approximate this integral in a very specific way. So what do? Well, we look at the integral and we replace v tau with the original, with the initial point of the integral. So we replace that with basically vt, okay, the initial value. Now, once we do this approximation, well, the integrand is basically a constant, doesn't change with tau anymore. So I can bring that out, take the integral, it will be 1, okay? And I'm going to reach to this update. This is precisely the update of gradient descent, right? So that's why we basically say that there is this association between gradient descent and forward Euler discretization. Now, this is not the only way you can discretize. Let's talk about the backward Euler discretization. And this turns out to be the proximal point method that we talked about previously. Well, I take this integral, and instead I'm going to approximate v tau with the last point. So I'm going to approximate it again with vt plus 1. Again, the integrand is independent of tau. It can come outside. The integral becomes 1. Well, I'll arrive at this update, which is precisely the update of the proximal point method. And as we mentioned, this is an implicit update. So in many cases, it is not desirable to use this strategy. All right. So let's talk about another kind of discretization. Well, we replace v tau with the first point and the last one. Nothing stops us to replace that with any point in the middle. Okay. So for any u between t and t plus 1 in this interval, you can basically do the same approximation. In particular, let's take the midpoint. Okay. So let's set u to be 1.5, and again we do the same thing. We arrive at this point. We haven't done anything. Again, it doesn't even mean, it's not even clear what we mean by the function value at the midpoint. But what we can do is to actually now approximate the update rule for the midpoint via the forward Euler discretization to get an explicit update. Okay. So what do then? We basically apply this extra gradient method. The name extra suggests that we are basically taking two gradients. Okay. We first apply the original gradient descent idea to go from the current solution to the midpoint. And secondly, we take another gradient to update the original solution Vt by the direction given by the gradient of the midpoint. Okay. So this is basically called the extra gradient method, and the idea is that extra gradient method tries to basically approximate the gradient at future t plus 1 with approximating the future point and finding the gradient. So that's what it tries to do. Okay. So it is widely now known in the literature that again the relationship between extra gradient method and proximal point method. Here I'm showing a result from the researcher that basically shows for a specific simple, let's say, bilinear game, the trajectory of the proximal point method and extra gradient are very, very similar. So as we can see here in this plot, the black curve here, this corresponds to the gradient descent. It diverges, it doesn't reach the equilibrium, whereas the other curves, the other trajectories, namely for proximal point method, extra gradient, as well as optimistic gradient, something that I'm going to talk about in the next slide, all converge to the equilibrium. Again, this can be associated with the idea of the negative momentum, that we are sort of correcting the wrong momentum, wrong direction of the gradient by using the predictability. Okay, so this is therefore the second method in terms of algorithmic ideas for min-max problems that arise in the context of GAN training. Compared to the proximal point method, which was implicit, extra gradient method is an explicit method. Now there is another approach which is also quite elegant and popular and useful, and that's basically called the optimistic gradient descent. It can also be viewed as an approximation to the proximal point method. Okay, so to show or motivate optimistic gradient descent and the name optimism basically, let's consider that we have a field, capital F, which is Lipschitz. So that means that the variations are controlled, such that approximately the gradient, let's say at time t plus 1, is approximately the gradient at time t. And naturally this approximation becomes tight or loose depending on how Lipschitz the gradient is. Okay. All right. So if we use this simple approximation, zero-order approximation, if you will, then we basically recover gradient descent. Okay. So the future gradient is something that we use in proximal point method. If we naively approximate it with the current gradient, we get gradient descent, which is not going to work. Okay. So what do? We're going to try to get a tighter approximation by, if we will, doubling down on our optimism towards the fact that F is Lipschitz and the variations are controlled. In particular, the idea is that instead of writing the zero-order approximation or zero-order Taylor approximation, let's write the first-order Taylor approximation. It will look complicated. Now we're gonna again make some assumptions and be optimistic, such that we can sort of again find a nice, simple-looking update. Okay, so that's the main idea. So let's start therefore by considering the first-order Taylor approximation of the gradient at the future. Okay, so if I write that down, it's basically the current gradient times the inner product of the Jacobian and the difference of next point and the current point. Okay. All right. So this is not a simple update. The Jacobian of F is a big matrix, so we can. It's not going to be quite efficient to use that in practice, particularly in scenarios where we are training deep plane models. So, for instance, if each of my networks have millions of parameters, this Jacobian is going to be something which is million by million, or the million by the million. So it is a very huge matrix. Okay, so we'll try to approximate that, approximate the Jacobian. Okay, so this is where for instance, we can double down on our optimism. Okay. Okay. So we're gonna approximate the Jacobian in this form. In particular, we're gonna consider this rank 1 approximation because this is just the outer product of two vectors. Okay. And again, this is somewhat intuitive to see when you compare it with again the approximation of just scalar derivatives. Okay. So for a scalar derivative, we're gonna say that, let's say, if I have a function h prime, if h, and I'm interested in this in this derivative, well, this is approximately h at w plus, let's say, epsilon minus h of w divided by epsilon. Okay, so this is essentially what we are doing in the right side of the equation 26, but we are doing that for a matrix. Okay. All right, so here E is basically a unit vector in the direction of the difference of Vt and Vt minus 1. All right, now lastly, what I'm going to do, I'm going to again assume optimism. Okay, so let's try to optimistic one last time and assume that the difference is kind of preserved as you move forward in time, such that the difference of the current and the next solution is roughly the same as the difference of the previous solution and the current solution. So if I make this assumption and be optimistic and put everything together, well, this is going to be my approximation of the future gradient. So by Taylor expansion, we had with this inequality, we have this approximation. So let's use the approximation of the Jacobian and the fact that I'm assuming that the differences are preserved over time. So if I plug that in here, well, I'm gonna get this complicated looking quantity. But the idea here is that in the denominator, I have essentially Euclidean norm square of the difference between Vt and Vt minus 1. In the numerator, I have the inner product of Vt minus 1 with itself, which is essentially the Euclidean norm square. So the two terms in the numerator and denominator will cancel, and I'm going to be left with this simple looking update. Okay. Well, this is saying that I'm going to sort of approximate the future gradient with something like this. And here is how you can see where the negative momentum term comes from, where we are moving still in the direction of the current gradient, but we are subtracting from it this vector. We are introducing this negative momentum. Okay, so if I therefore use this in my update, I'm gonna arrive at this equation. So it says that go from the current point to the next one by following this specific update vector, which has a term in the direction of the current gradient, okay, and have another term, a negative momentum term, which tries to fix the issue that arises from the skew symmetric nature of the dynamics in min-max problems. So therefore, we talked about a few algorithms with the hope of correcting the dynamics and making sure that when we train generative adversarial networks through min-max optimization, we can actually reach the equilibrium. And these methods indeed can reach the equilibrium under certain assumptions. Nonetheless, it is a very interesting and popular direction of research to basically expand the frontiers of these algorithms, make them more efficient, and understand what are the assumptions and conditions under which these methods can find the equilibrium or cannot find the equilibrium. All right. So with that, let's end this lecture, and I'll see you next time.